Alright, now we are going to create a box plot. And in order to create the box plot, what we first need to do is we need to find the 5-number summary for the data set. So what we're going to do is we're going to do a box plot for Kevin Durant's January 2013 numbers here, scoring numbers. Um, we've seen this set already. So let's get started. The first of our numbers in the 5-number summary is the minimum value. Now, since we already have the order statistics for this data set, it's going to be quite easy to find the minimum value. It turns out that the minimum value is really just the first order statistic, which we symbolize this way. So the first order statistic is the first number in this um, ordered list, which is 20. So turns out that our minimum value, or the smallest scoring output, is 20. So that's the first number of our 5-number summary. The second number in the 5-number summary is the first quartile. The first quartile we're going to denote as Q3. Oops, Q1. Sorry about that. It's the first quartile, so we're going to actually denote it Q1, the first quartile. And this is actually a percentile. The first quartile is actually the 25th percentile. So we're going to calculate our 25th percentile, and that's the number we're going to use as our first quartile. So the first quartile is calculated this way. First, we have to do the locator, L. So we'll find the locator, L, and L is just equal to the value of K, which in this case is 25, times N, which in our case is 16, all over 100. So this is kind of like multiplying the percentage form of our percentile, or sorry, the decimal form of our percentile by the sample size n. So this is going to be 25, which is k, multiplied by 16, which is n, divided by 100, which gives us the number 4. So L is 4. Our locator is 4. And since L is a whole number, if you remember from the percentile video, since L is a whole number, what we actually have to do is we actually have to to find the 25th percentile, which is the first quartile, what we're going to have to do is we're going to have to take the 4th order statistic. We just found L to be 4. Since it's a whole number, we're going to have to take that order statistic and the 5th order statistic, the next one in line, the 5th order statistic, add them together and divide by 2. In essence, we are averaging the Lth and the L plus 1th order statistic. So in our case, that turns out to be 26 plus 26 over 2. You see, we are taking these two order statistics, the 4th and the 5th one. This is x4 and this is x5. They're both 26 and we're averaging them. So we get that the first quartile is actually the number 26. So we can put that here. The first quartile is 26. And now we move on to the median. Well, the median, we had a video that showed us how to find the median of a data set. And the median really is just the 50th percentile. So the median is the same thing as actually the second quartile. It's the second quarter of the data. And we're seeing that that's also the 50th percentile. So the median is calculated as a percentile. We find L, the locator. We take 50, which is K. We multiply it by 16, which is N. And we divide that by 100. And once again, we get a whole number. We get 8. So it turns out that the median is actually the average of the 8th and 9th order statistic. Well, here we have the 8th order statistic. This would be x8, the 8th statistic in the list of ascending magnitude. And this is the 9th order statistic. So we're going to average the 8th and the 9th order statistic, 29 and 32. Well, let's see. So we're going to take, for our second quartile, we're going to take x8 and add it to x9, the 8th and 9th order statistic. We're going to add those two together and divide by 2. And in our case, we have 29 plus 32 divided by 2, and it turns out that our third number in our five number summary, the median, is actually 30.5. So that's the number we're going to use for our median when we construct our box and whisker plot. So let's see. The second quartile, or the median, is 30.5. Okay, now we're going to calculate the third quartile. And the third quartile is, as you can probably guess already, the third quartile is denoted Q3 and is actually the 75th percentile. 75th percentile. And let's find out what that value is. Well, first we need to find our locator, L. L is equal to, in this case, since we're looking for the 75th percentile, K is 75, N is still 16, and we're still dividing that by 100. And this gives us the number 12. So the locator is 12, which means to find the third quartile, Q3, I'm actually going to average the 12th and the 13th order statistic. That's the 12th and the 13th order statistic added together and divided by 2. So let's see if we can find the 12th. Well, the ninth was 32, 10th, 11th, 12th. The 12th order statistic, this 12th order statistic, x12 in parentheses, is 35. And the 13th is 37. So what we're going to do is we're going to take 35 and add to it 37 and divide that by 2. And it seems like our Q3 is actually the number 36. So the third quartile is 36, and that is the fourth number of our five number summary. And last but not least, we have the maximum value. Well, the maximum value is really just xn, whatever the value of n is. And in our case, like we've been saying, n is 16. So we're looking at the 16th order statistic, or basically the last value in this list. So this is x16, the 16th order statistic, and remember x1 was our minimum. And it turns out that the maximum value is 52. So now we've calculated our five number summary. We can also calculate another measure that will be useful for making our box plot called the interquartile range. And if you notice here, the interquartile range is going to be the third quartile minus the first quartile. So let's see what we get here. Well, the third quartile is 36, and the first quartile is 26. So the average of 36 and 26, or sorry, the difference of 36 and 26 is 10. So it turns out that our interquartile range is going to equal 36, which is Q3, minus 26, which is Q1, and this is equal to 10. So our interquartile range is equal to 10. Now, the reason why we wanted to calculate the interquartile range in the first place is because we would need to be able to identify outliers. So let's talk about outliers. A data value is an outlier if it is above Q3 by an amount greater than 1.5 of the interquartile range, IQR is the interquartile range, or below Q1 by an amount greater than 1.5 of the interquartile range. So basically what we're doing is we're setting up boundaries around our data set, and any data value that falls outside of those boundaries we're going to call a outlier. So let's see if our data set has any outliers. What we need to do is we need to calculate these numbers. So let's see the lower end. It says that if a number is below the first quartile by an amount greater than this much, then we have to call that value an outlier. So let's calculate that. Let me see, 1.5 times the interquartile range. Well, 1.5 times the interquartile range is equal to 1.5 times 10. And 1.5 times 10 is 15. So 15 is a number that we're going to use as 1.5 times the interquartile range. So basically, a number is an outlier if it is smaller than Q1 minus 15. Q1 is 26, and 26 minus 15 is, let's see, that is 11. 26 minus 15 is 11. So any number in that data set smaller than 11, we're going to use as an outlier. So 11 is the lower bound. Now let's take Q3 and add to it 1.5 times the interquartile range, which is 15. So that is going to be 36 plus 15, which is, let's see, that seems to me to be 51. All right, so this number is going to be our upper bound. Any number greater than that, we're going to say is an outlier, and we are not going to use that as our, we're not going to use that number to create our box and whisker plot. We're actually going to graph that number, but it's not going to be a part of our box and whisker plot or our box plot. All right, so now we know all the information we need. We know where each one of our quartiles, our minimum and our maximum is, basically this 5-number summary. And we also know that one of our data points is an outlier. Let's take a look back at our data set here. Let's take a look back at the data set and see what the outlier is. Well, if you come back down here where we define the outlier, any number smaller than 11 and any number larger than 51, we're going to consider an outlier. So looking at our data set, the smallest number here is 20. So there's no number that's an outlier because it's too small. But the largest number here is 52. And remember, 51 was our cutoff point for a number to be an outlier. So the number 52 is actually an outlier. It's an extreme value. And we're going to have to take that data point out in order to create our box plot. So we need to modify our box plot. We need to get rid of the outliers. So we're actually going to modify here. Instead of using 52 as our maximum value, we know that 52 is not our maximum value because it's an outlier. We're going to use the maximum value of 42. So now we are going to create our box plot. All right, so let's extend this page. Extend. All right, so to create our box plot, the first thing we're going to do is we're going to create a number line. And on this number line, we're going to mark it so that we can fit all our data values. Well, we need to put data values from the minimum to our maximum. So we need to put data values from our minimum to our maximum. But actually, we're going to go all the way up to our old maximum of 52. And I'll show you why in a second. So what I'm going to do is I'm going to start at 20 as the left end here. And I'm going to count by fives all the way up until I get to 55. So that's 20, 25, 30, 35, 40, 45, 50, 55, and actually let's make these a little wider so we can get a little bit more on here. So let's start once again at 20, then we have 25, 30, 35, 40, 45, 50, 55, 60. So we're going by fives here from 20. So 20, 25, 30, 35, 40, 45, 50, 55, and 60. And I tried to make these as evenly spaced as possible. So this is how we're going to create our box and whisker plot. The first thing we're going to do is we're going to create a small vertical line above our minimum value. So we're going to take our minimum value and we're going to graph it. So here's the minimum value, x1, the first order statistic, 20. We're going to come down here and we are going to, above our number line, make a vertical line right above the 20. That's where the first whisker is going to end, or begin, sorry. Now, we're going to go to our next number in our five number summary, 26, the first quartile, and we're going to make a vertical line above that number also. And that vertical line is going to be slightly bigger than the first one. So we're going to go to 26, which is somewhere in here. We're going to make a vertical line right above there. Okay, so now we have our vertical line above our minimum and above our first quartile. And we're going to also do the same thing for the rest of the five number summary. So the median is 30.5. So I'm going to make a vertical line above 30.5, the exact same size as this one. So I'm just going to go ahead and put that above 30.5, which is here somewhere, about 30.5. And I'm going to do the same thing for the third quartile, which is 36. So 36. So let's see. Let's make another one. And above 36, we're going to make this one. And there we go. 36 is right around there. And then we're going to make another vertical line, another small vertical line above our maximum value. And our maximum value in this case is 42. So 42 is going to be a vertical bar, but that vertical bar is going to be the same size as our minimum. So we're going to go ahead and create a box plot here. Create a vertical line, same size as this one, and we're going to put it above our uh, maximum, which is about 42. So this would be the skeleton of our box plot. Now all we need to do is connect these vertical bars that are the same size in the middle to create a box. And once we've created that box, then we're going to extend horizontal lines from our maximum and minimum point to create the whiskers of our box and whiskers plot. And here we've created our box plot. This is actually a modified box plot where all the outliers are taken out. So what we want to do here is we want to show that extra value, the maximum value that we said was an outlier. We want to actually show it as a dot outside of our box plot. So this would be the modified box plot actually for our data set. And it shows that Kevin Durant's output is pretty symmetric. I mean, it seems as though this whisker is longer, so this distribution seems to be slightly skewed, but not much. This is a pretty symmetric distribution because the two whiskers are about the same length, and the middle line of the box is about the same distance from the two outer lines of the box. This is the modified box plot where we take out the outliers. Let's go ahead and let's create a box plot that's not modified, a box plot where we're not taking into consideration the fact that that value of 52 was actually an outlier. So let's create a non-modified box plot. And to do that, we're going to go ahead and we're going to make a new number line. Well, actually, we can use this same number line. Underneath this number line, I'm going to create what is called a normal box plot, and we're going to compare that to our modified box plot. The only difference between a regular box plot and a modified box plot is whether we keep the outliers or not. If we keep the outliers in the data set and create that box plot with the original maximum, we're going to get a box plot that looks slightly different and is going to give us a slightly different interpretation of what the data is. Let's go ahead and do that. So once again, all the other lines are going to be the same. The vertical line that goes above the minimum is going to be the same. Oops, let's undo that. Matter of fact, since we're making the same vertical lines, let's just go ahead and use the original ones here. So this vertical line would be the same. So let's clone that one. We're going to make the modified box plot underneath here, or the original kind of box plot, not the original kind. We're going to make the regular kind of box plot underneath here. So I'm going to make a vertical bar above the minimum. I'm going to make another vertical bar above the first quartile. So we're going to clone this also. And the first quartile is the same here. We're going to make another one above, or not above, now we're below. We're going to make another one below the median, and we're going to make another below the third quartile. And now this is the only difference between a regular box plot and a modified box plot. That last vertical bar that we're going to make, that's the same size as this original vertical bar, we're not going to make it above 42, which would be the modified maximum. We're going to make it above 52, which was the original maximum. So if we put it way out here, where 52 is, and if we create this box and whisker plot, or this box plot, that's not the modified version, then we get a box and whisker plot that looks something like this, where if you see this whisker is a lot longer than this whisker on the right is a lot longer than the whisker on the left. Now, looking at this box plot, this would tell us that this data set is skewed to the right because the whisker on the right is a lot longer than the whisker on the left. But you see, if we get rid of outliers, we get a box plot that more closely resembles the actual data without the extreme value that is an anomaly. But if you look at the not modified box plot, the one on the bottom seems to imply that this data set comes from a population that is skewed to the right, meaning there are some values that are a lot larger than other values, and making this distribution not symmetric. But it turns out that if you look at the modified box plot, this scoring distribution is actually pretty symmetric.